All right, back with thin films. I would like to go through now as an exercise of trying to figure out this. We have now an additional variable in that before with the double slit apparatus, you had path 1, path 2 minus path 1 was d sine theta. When that was equal to m lambda, you had maxima. When that was equal to m plus a half lambda, you had minima. Now we're splitting the beam in a different way. We're causing part of the beam to go up top of the film, up bottom of the film, and that 2tn is the extra path covered by one relative to the other. That's our path difference. Typically, if that was equal to m lambda, we get maxima. And it was equal to m plus a half lambda, we get minima. But now, because of this additional variable of a ray potentially flipping phase, right? So if one of these guys that we look at upon reflection or transmission has undergone a differential phase shift of pi relative to the other, right? Then whatever was maximum becomes minimum, whatever was minimum becomes maximum, and we have to keep track of that. So we have to go through a little exercise now of figuring out some phase shifts. So say there's n equals 1, n equals 1.3, n equals 1.5, and what I'd like you to do is assign phase states, call them phase states, to the rays that go through. So this is equal to n1.5, and 1.3, and equals 1. And we have here, for example, n equals 1, n equals 1.5, and n equals 1.3 on this end. So what I'm going to draw for you is beams, typical, beams for interference. Let me color them differently with green maybe, right? Green laser, right? So, right, and this is that, okay? What you're gonna do now on your own is pause the video, jot this down on a piece of paper, write these things, draw these things on a piece of paper, and I'm gonna draw arrows to indicate which way the beams are going. 1, 2, 3, 4, 5, 6, 7, 8, and here same, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay. What I'd like you to do now is starting with a phase 0. Like each of these rays starts with a phase 0, whatever that means. Okay. These guys have phase 0 to start with. Assign the phase states. The current phase state, like if one of these undergoes a phase flip of pi, put a pi on it. Okay. If for some reason one of them undergoes a phase flip of 2 pi, your pi plus pi gives you 2 pi, which is 0. Okay, so I'd like to put binary 0, 1, 0, 1 on these rays. So I know it's a slightly confusing discussion in that we used to say that if delta x is equal to m lambda, we get constructive. Now we have this additional phase shift of pi, and we have to put the two things together and come up with a concise, coherent way of looking at thin films, and then apply this concept to wedges. So for now, guys, I'd like you to pause the video, okay, and see what you can do with the phase flips. Which one of these are going to flip once? If they flip phase only once, based upon the indices of refraction, then you put a pi. If it flips phase twice, 2 pi, which is 0, you can put a 0 on that. So please do that now. All right, so continuing now. Upon transmission, that's the easiest part. There is no phase shift upon transmission, okay? So we'll assign 0, 0 to each segment of the ray here, all right? Now, this guy goes from 1.3 to 1.5, so 1 to 1.3 and reflects off the interface. So this is why we have a pi. Now this guy here, look at here, we have 0 here, and this one goes from 1.3 to 1.5. It has a pi phase flip and retains that pi phase flip. So these guys are in phase. So for these two, we say that when 2tn equals m lambda, we have maxima. Okay, that's the condition that we know because they both underwent the same phase flip. So it's like they didn't undergo a phase flip at all relative to one another. Okay, so here we have 0. Now this guy already has pi. Okay, a pi phase flip. Okay. We're looking at the current phase of the ray, not just the amount of phase flip it goes through by, not the amount of phase flip it goes through or it undergoes. The current phase condition, phase situation of this beam is pi. this will not incur, going from 1.3 to 1, it will not incur an extra phase tip. It will retain the pi, and this is pi as well. So down here, when 2Tn equals m lambda, we will get minima. Okay? Let's take a look at this one here. We have 0, 0, 0 all the way through. No phase tip. 1.5 to 1.3 reflecting no phase tip. This continues with a 0. And this goes from 1.3 to 1. So we have, again, no, if it retains is 0. And this one here undergoes, you know, when it goes from 1.3, this is 0, 1.3 to 1.5, there is a pi phase slip here that is maintained over here as well. Okay? And let's look at these guys here. So had one of these guys underwent 2 phase flips for some reason, like, going from, let's say this was 1.4 here, then you'd have an interesting situation in that, maybe we'll do that next, okay? So this is 0, and upon reflecting 1 to 1.5, I have a pi, 1.5 to 1.3, I have, this is still 0, 0 here, and I have, so typically, if you have, you see always, if there is 0, 0 or pi, pi, there'll be a 0 pi down here, right? So, if you're using condition number 1, which says that 2Tn equals m lambda is maxima, then you use condition number 2, which is that 2Tn equals m lambda is minimum or destructive interference. Okay. There is one more case I want to take up with you to show you what happens when we have array undergo 2 phase flips in the process. So as my thin film here, okay, and I'll have to design this so that it gives you what I want. There's going to be 1.5, there's 1.3, and this will be 1.4. And I would like you to do now, guys, just on your own. Okay, again, pause the video now and see if you can assign the phases to these rays. Right? So this begins with 0. What would these look like in this case? So please pause again now and write down what you think the phases should be. So this is 0, 0, 0. We go from 1.5 to 1.3. Reflection, yes, but from higher to lower, no phase flip, maintains a 0. 1.3 to 1.4 reflecting, I have a phase flip of pi, and that is maintained up here. And 1.3 here, this ray goes from 1.3 to 1.5. Reflects, there is another phase flip. This is important now, guys. This pi, this phase state of pi, when you reflect here, you have another pi that's 2 pi. That's the same as 0. So I'll say 0 here and 0 there. So here, if we're looking at interference in transmission, we say that 2Tn equals m lambda gives us constructive interference, and 2Tn equals m plus a half lambda gives us destructive interference. These are the conditions that we're used to. And these are the new conditions. This is the new condition now, that if 2Tn equals m lambda, I get now destructive because of the extra phase slip. And if 2Tn equals to m plus a half lambda, I will get constructive interference. Okay? So you play games with that and find, for example, you construct some stuff whereby you have an index of refraction of 1.5 or whatever, and the wavelength of whatever it might be. What are the thicknesses that would allow you to have constructive and destructive interferences, in transmission and in reflection? Okay? So we're going to pause here and continue with wedges shortly.